So for this video, we're going to be talking about angular momentum, the equation for it, and then go over example problem number 32. So we'll get right into it. So angular momentum is defined as the quantity of a rotation of a body. And we should remember that angular momentum can be denoted by P, and that when it's not in rotation, we talk about it as mv, but because it is rotational momentum, angular momentum, the equation is going to be IW, and we denote it, the angular momentum, as L. So that's something we want to remember and write down. So now what we're going to talk about, we're going to go right to the problem. So it's the second part of this problem. A particle of mass m moves counterclockwise around a horizontal circle of radius r as shown above. The angular speed of the particle is given as a function of time t by omega t equals bt, where b is a positive constant as t is greater than 0. So for angular momentum, we have the equation, and I'm going to just define these real quick. This is moment of inertia, or rotational inertia, and the equation for this is mr squared, and the equation for omega, or angular velocity, is v linear velocity divided by radius. So that's going to give us what we want, but real quick, we're going to use this in our problem. So it's asking, what is the magnitude of the angular momentum of the particle about the center of the circle as a function of time? So they already gave us the equation for omega t, or angular velocity, as a function of time. So we're going to use that to get, we already have the equation for omega, which is just bt. So we can use that. And now to find L, which is angular momentum, we're going to need to find I, which is the moment of inertia. And remember that also equals mr squared, or the integral of r squared dm. So we're gonna just plug that in. So we have this. The problem doesn't ask us to find specific values for m or r, so we can just plug that in. As you can see in the model, it just gives us an r for that. So we can just plug that in for I. So I equals mr squared. So we have L angular momentum equals bt times mr squared. So that equals m times b times r squared times t. We'll put t at the end because it asks it in terms of a function of time. So that's what we got for our angular momentum as a function of time. So here's our answer. And now they ask us, let's see if that matches up with any of our answer choices. Nope. A is a no. B is a no. C, there we go. MBR squared times T. That's our answer choice. And now I just want to remind that the equation for angular momentum equals moment of inertia times angular velocity, and that's really all we had to use here, as they gave us right here the equation for angular velocity, and then all we had to do was plug in what the moment of inertia was, which is just mr squared. So that was pretty simple, and that's that. C is our answer.